For many years, BICC Pyrotenax mineral insulated cables have been used extensively worldwide in situations where their unique properties make them the ideal choice. They're easy to install, water, oil and gas tight, fireproof and extremely robust. So popular are they, in fact, that every day electrical engineers worldwide are installing many hundreds of thousands of meters of them. Well, that's an awful lot of cable, and it all has to be installed correctly. So just how do professional engineers go about the job of installation? Well, the methods will vary according to the particular project and, of course, to the site. And in order to establish a standard of installation practice, we asked NG Bailey, one of Britain's largest electrical engineering and contracting companies, to tell us how they train their students in the use of Pyrotenax cables. I have with me now Alan Walker, Associate Director and Craft Training Manager for NG Bailey. He's responsible for the recruitment, training and welfare of all the company's apprentices nationwide. Alan, I think it's generally recognised that your company sets a standard of excellence in training electrical engineers that's pretty hard to beat.
Well, we certainly like to think so. The training programmes that we run cater for an annual intake of approximately 140 students. Each student completes 24 weeks of off-the-job training during each of the first 2 years. 12 weeks each year are normally spent at one of our own training centres, with the balance being spent at the local technical colleges. We do pride ourselves on providing these young people with training of an extremely high standard. It benefits their own future careers and ensures that we as a company have personnel with a comprehensive range of skills suitable for the wide variety of projects they are likely to undertake working for Bailey's.
So does working with mineral insulated cable form a significant part of the training?
The initial study of MI cable installation takes place in the student's first year, and then we expand on it in the second year. The time spent on this subject is quite considerable and combines classroom-based theory with practical exercises in installation. It's a significant element in the training programme and forms a key part of the students' formal examinations at the end of training.
Talk me through the practical aspects of installation. Perhaps you could bring out the points that you'd emphasise to the students. It's probably a good place to start. The arrival of the cable on site from the local wholesaler. How is Pyrotenax cable handled on site?
The cable arrives either in coil form or on reels. The popular sizes are normally supplied as 100 metre long, half-metre diameter coils. We emphasise that it is important to avoid kinking the cable when placing it in position by simply keeping it straight as it's being rolled out. If the cable is in coil form, then it can be rolled out along the route, or a payoff reel may be used. If the cable is supplied on plywood reels, then these can be placed on drum stands for easier handling, and then the cables can be easily pulled off. It is important to avoid abrasion from rough ground on site. MI cable is handled like any other cable when it comes to pulling it through ducts or installing it on cable tray.
Presumably you have to train the students about various different kinds of installation.
Yes, we train them so that they can fix the cables correctly in all locations. Students have to be fully conversant with all types of surface mounting, installations on cable tray, installations in ceiling voids, false ceilings or floors, how to bury the cables in plaster, concrete or underground.
I can see that cables sometimes have to follow very difficult routes. Do the students receive any training in the use of tools for these purposes?
Well, the majority of MI cables are easily bent by hand. To produce perfectly neat, symmetrical bends, our students practice the use of the roller straightener and the bending tools to help form the cable prior to fixing. Students also practice final dressing of the cables using a soft face mallet.
Well, we've seen some Pyrotenax cables being fixed. What are the points about fixing that you need to consider?
It is feasible to fix the cable with plastic cable ties and clips similar to those used with plastic cables. However, it is more common practice to secure the cables with metal fixings, either single-way clips or two-way saddles or copper fixing strip for multiple cable runs. We draw our students' attention to the fixing distances specified in the relevant table of the IEE wiring regulations. This shows MI cables require fewer fixings than plastic cable. It's a cost saving.
When I've been shown site work, I've sometimes seen long lengths of cable, quite extensive amounts really, left at termination points. Is this absolutely necessary?
No, it's not, and as it is important to minimise wastage on site, we train our students carefully in this respect. When MI cables are cut and the insulant exposed to the atmosphere, then moisture will enter the cable. Sometimes it's a misconception that the moisture will penetrate a long way into the cable. This is not true. Even after many months exposure, moisture will not penetrate more than 200 millimetres into the cable. The installer therefore only needs to allow sufficient cable to form the conducting tails. Leaving more is wasteful and unnecessary. For the same reason, there is absolutely no point going to the cost and trouble of temporarily sealing the cables which are intended for storage.
Right, now we've got the cable fixed. How do we terminate it?
Terminating is an easy procedure, but one that must be understood and performed correctly. We train our people using what is called a standard termination. This incorporates a seal and a gland, and the seal separates and insulates the conductors and prevents moisture ingress, and the gland is for mechanical entry and earthing.
And does the standard termination cater for all situations?
Our students are trained to work on all types of projects: oil and petrochemical, commercial, industrial, public and private sector, and can use MI cable systems in any environment without any additional training. Usually the standard gland and seal is suitable, although they are aware that other glands and seals are available for non-standard applications.
Well, thanks very much indeed, Alan, and of course our thanks to NG Bailey for giving us the opportunity to visit one of the training centres. Well, we've seen how the experts trained their students. Now we're going to look in detail at the recommended procedure for terminating Pyrotenax cable. In order to explain the basic principles of terminating, we're going to look at a 20mm standard termination. The techniques involved are common throughout the range, although they vary slightly depending upon the type of seal or the number of conductors. Written installation instructions are available for any BICC Pyrotenax seals on request. A complete termination consists of a shroud, compression gland and seal. Whilst a seal must always be used, the compression gland and shroud are optional. For example, a compression gland would not be used with cable grip type terminal boxes. Let's now consider how these are fitted. It's advisable to cut the cable with a hacksaw, since this will later facilitate stripping the copper sheath. If the cable is plastic covered, then a plastic gland shroud will normally be used. This is best fitted by offering it up to the cable in reverse. It's then simple to determine the amount to cut off, thereby ensuring a tight fit over the cable. The shroud can then be slid over the cable in the correct fashion. The next stage is to remove the plastic covering. Mark the covering to the correct tail length, plus an additional 70mm to allow for the gland. This additional length will vary depending upon the gland size. From this point, remove the plastic covering with a knife. Don't use the edge of the blade at right angles to the cable, as this may damage the copper sheath. After removing the plastic covering, the copper sheath is stripped back. In this case, we will use the joy stripper. In order to remove the correct amount of copper sheath, mark off the tail length plus 11mm, point A. This additional amount will again vary depending upon the seal size. Add a second mark, point B, a further 1 tool's width along the cable. Insert the cable into the joy stripper tool until the end just touches the cutting blade. Beginning with forward pressure, rotate the tool clockwise. Forward pressure is not required once stripping has begun, since the tool will pull itself along the cable. Stop the tool at the required position A by gripping the cable with pliers at position B. The gland should now be slid onto the cable. It consists of 3 parts: a back nut, compression ring and gland body. The seal can now be fitted. This comprises a brass pot, plastic stub cap, PVC insulating sleeving and grey sealing compound. The pot has a self-cutting thread which enables it to be screwed onto the cable, using pliers, a pyro potter, or, as in this case, a pyro wrench. Insert the pot, open end first, into the pyro wrench recess. Slide over the cable until the self-cutting thread is in contact with the cable sheath. Engage the ratchet wheel into the knurled section of the pot. Applying forward pressure and a cranking action, screw the pot onto the cable. This section, through a seal, illustrates the correct position of the pot, with the inside base level with the end of the cable. Incorrect positioning of the pot will make it difficult to fill with compound. If the pot has an earth wire, position it equidistant from two adjacent conductors. After fitting the brass pot, examine the interior, beware of eye damage from the exposed conductors, and remove any loose insulant. Slide the stub cap over the conductors and into the mouth of the pot to pre-form the conductors. Then partially withdraw it. The pot should now be filled with grey sealing compound. It's essential that this compound covers the face of the cable, thus effectively sealing the end, and hence preventing the insulant from absorbing moisture. This can be achieved by overfilling the pot with compound from one side only to exclude air pockets. Care should be taken to avoid contamination of the sealing compound, so use the plastic wrapping to keep it clean. Reposition the stub cap in the mouth of the pot. Don't let it overlap the edge of the pot, since this will damage the thin brass lip during crimping. Two types of tool are available for crimping the disc into place. We shall use the pyro crimp. Fully slacken the hollow drive screw by means of the handle. Slide the conductors through the hole in the crimping plate and through the centre of the drive screw. Place the pot into the seating in the body of the tool. Tighten the screw by hand, which will drive the stub cap fully into the pot recess, and secure it into position by means of the indent crimp. Slacken and remove the tool. Cut the stub sleeving to the required length. Slide it over the conductors and then push it onto the stub to anchor it in place. Identify the conductors. Connect the gland into the box, ensuring that the nut is sufficiently tightened to grip the cable. If the covering has been selected because the cable is being used in a corrosive environment, then any exposed copper sheath and brass gland must be covered with adhesive tape before positioning the gland shroud. The termination is now complete. That's the recipe then for a perfect termination, but is it really as simple as that? Peter Malone from Pyrotenax is here now to answer the most common queries that people raise. Peter, I know that the standard seal suits most applications, but you do offer a full range, so under what conditions would you use the others?
Well, the standard seal operates between -80 and 105 degrees centigrade, and this is generally sufficient for the vast majority of installations, but in addition we do have seals for high temperatures, nuclear applications, potentially explosive atmospheres, and of course for fire resistant applications.
Well, it's certainly a comprehensive range. Now, what about glands?
Well, you only need one gland. The standard externally threaded gland is suitable for all the applications we've mentioned. However, where there are space limitations within the terminal box, Pyrotenax can supply an internally threaded gland. This is called a Space Ranger, which comes in two sizes and covers the full range of popular light-duty cables.
Now, subject of testing, do you really have to test the cable before you install it?
No. The ICC Pyrotenax cables are fully tested at the factory and are BSEC approved to BS 6207. This approval ensures that the cable has been manufactured in accordance with the standard and also checked by independent inspectors.
And what insulation resistance should you expect after installation?
After both ends of the cable have been terminated, we would expect that the insulation resistance would be in excess of 100 megohms. However, initial low readings are not a cause for concern, and the insulation resistance should be noted and a second reading taken 24 hours later. A higher second reading indicates that the cable has been correctly sealed and the value should now be at least 100 megohms. If the value has not risen or has fallen, this indicates a fault condition, and this should be located and rectified.
Well, if the reading isn't 100 megohms after 24 hours, what should be done?
There's a simple test to establish whether the cable has been sealed correctly. Firstly, connect an insulation tester between two conductors, or one conductor and sheath. Then apply a small amount of heat to the cable behind the seal using a match or a cigarette lighter. A rapid fall in the reading confirms that the seal is faulty. If there's no change, then the seal is good. Where it's not practical to use a naked flame, a similar test can be done using a freeze spray. However, in this case, the reading will rise if the seal is faulty, and it should be noted that this increase in insulation resistance is not permanent, and it will return to its previously low value as the cable returns to room temperature.
Can you repair a badly made seal?
Yes. First, remove the faulty seal and strip back 3 or 4 millimeters to remove the threaded sheath. Then clean the cable and re-terminate as previously demonstrated. Although the insulation resistance will still be low, if the end has been sealed effectively, the reading will slowly improve until it exceeds the 100 megohms.
What are the common mistakes that are made with sealing?
Well, if the pot is incorrectly filled, an air gap is left at the face of the cable. This will allow moisture from the atmosphere to travel along the pot threads into the cable, resulting in poor insulation resistance readings. Not screwing the pot on sufficiently can produce a similar result, and if the pot is screwed on too far, then a direct earth fault may result.
Is the fact that the insulant will absorb moisture really a problem?
No. Provided the cables are sealed correctly, the insulation resistance will be maintained. If the cable is damaged during installation, this may produce a potentially dangerous situation, but with Pyrotechnics cable, the insulation resistance would drop, indicating that something was wrong, so therefore it can be said a Pyrotechnics cable is actually self-monitoring.
When I was talking to Alan Walker, he made what seemed to me to be a very valid point about fixing distances.
Yes. The IEE wiring regulations allow for the fact that MI cable is more self-supporting than other types of cable, which require some 2.5 times more fixings. As Alan stated, this shows an appreciable cost saving when surface wiring Pyrotechnics cable.
Now, the latest development in the Pyrotechnics range is this new twisted pair mineral insulated cable for data communications. Is this difficult to terminate?
No. Termination of twisted pair cable is exactly the same as for standard cable, except that the conductors must be untwisted and straightened before fitting the seal.
The twisted conductor cable is normally red with 2 grey stripes. What's the significance of this?
Well, the grey stripes distinguish it from the red standard pyro cable. The standard cables are available in bare copper or plastic coated for reasons of corrosion protection, aesthetic appearance or circuit identification.
Now, what about standards and approvals? Does BICC Pyrotechnics cable meet all the relevant national and international standards?
Yes, it certainly does. There's no constraint on using the cables virtually anywhere in the world.
Finally, Peter, it's a fact that BICC Pyrotechnics is a leader in world markets. It's a system that enjoys universal popularity. Is that because of some unique performance characteristics?
No other cable can provide the combination of advantages that Pyrotechnics does. Its solid construction provides an inherent flame-proof barrier. It will not burn or support combustion. It will not emit smoke or toxic gas. It will operate at temperatures up to the melting point of copper, that is 1083 degrees centigrade. It's non-aging, radiation resistant, virtually indestructible. It's smaller than other cables of the same current carrying capacity. It's pliable, waterproof and very strong, and the copper sheath provides an excellent low resistance to earth continuity.
That's a very impressive list, Peter. Thank you very much for answering all those questions. By following the recommended procedures and by bearing in mind the points we've discussed, you'll find that working with Pyrotechnics cable is both easy and straightforward. So do the job right and do it with Pyro.
To do any job correctly and safely, The appropriate tools have to be chosen, and those tools must be in good working order. Personal hygienic and protective measures prescribed for the job must be carried out before starting. These cables are frequently terminated in switches, sockets and consumer units in tunnel terminators. An insulation sleeve is placed on the bare earth conductor. Enough spare length of cable must be allowed for a second termination if required at a later date. The conductor ends are doubled up to fill the tunnel connectors and achieve better contact. The lugs are secured with a manual compression tool. The conductor must be placed right into the lugs, and its end must clearly be seen before the tool is operated. To achieve a good termination on this steel wire armoured cable, compression terminators are used. These are fitted with the help of a handheld hydraulic compression tool. The insulation may be cut and stripped away using a knife or a stripping tool. If a knife is used, care must be taken to cut away from hands or body whenever possible. The size of the die used in the tool is matched to the size of the compression terminal. The hydraulic tool is operated until the terminal is lightly gripped. After the terminal is in place on the cable, the tool is pumped to increase pressure until a click release operates. A trigger releases the pressure and the tool can be removed. manual compression tool can also be used to make the termination. For ease of use, this may be held in a vise. Once the size is set, the terminal is held in place and the cable end is fed into it. Smaller sized compression terminals can be secured to the cable ends with a hand tool. Some typical installations using compression terminals are connected in situ.
These brave fellas are live line linesmen. Their lives are on the line along with the job because they fix the power lines with the current on.
These men go about their daily business in close contact with almost 500,000 volts. So how do they do this without frying themselves alive? Well, the linesmen wear special protective suits. The garments are made of the same fire-resistant material used in racing drivers' clothing. Silver-plated copper wire is woven into the fabric. This channels any live current around the outside of the linesman instead of through his body.
That sounds okay, but there's only one way to be absolutely sure it works. Here at a laboratory in Leatherhead, a linesman is about to meet a hefty dose of electricity for the first time. Inch by inch, he's moved towards the huge electrical conductor until... You're not looking at a television special effect here. It's real lightning. This is what it looks like when a man is zapped by hundreds of thousands of volts.
I suppose it's similar to parachute jumping. And that initial jump of getting out the aircraft and that initial touch when you actually get 400,000 volts into you, it's just, you can't explain it really. You're there and you go, all of a sudden, you're there.
After the rehearsal, it's time for the real thing. But how do they get the linesman up and onto those power lines? By helicopter. This special machine must meet a strict list of safety regulations. It has 2 engines in case one cuts out, and the controls must not be affected by the electrical currents. The linesman is suspended from the helicopter by a special rope. Before going up, the rope is tested to make sure it doesn't conduct electricity. If current should pass from the line to the aircraft, the result will be catastrophic. With this in mind, the linesman is also tested for conductivity. The men are hoisted up the cables in cages, which are given stringent safety checks before takeoff. With a job as dangerous as this, the linesmen leave nothing to chance.
These highly trained pilots have over 10,000 hours of flying experience. They need it. To hold the linesman safely in position, they must hover on one spot 30 meters above the line without moving an inch. Not easy when you're flying a machine weighing 2.5 tons. And if that isn't difficult enough, the pilot is completely blind to what is happening below him. So how does he manage to place the linesman on the right spot?
I can't see the linesman. However, I have the mirror underneath, and I have him talking to me. And now he is the most crucial part of the operation. He is the guy who has my eyes underneath the aircraft. He will move me forwards and up and down, left and right, as he needs. And it is up to him to position me that final bit exactly where he wants me on the conductor.
Okay, going back to the leader.
"100 feet up with thousands of volts crackling past their ears, the linesmen set to work. Today they're replacing old spacers between the lines with new ones. It's just one example of the many small but vital jobs the linesmen must perform. The job finished, the linesmen leave as carefully as they arrived, and nearly 500,000 volts reach out to remind them why they take such care. Even with everything going smoothly, danger is never very far away. A chance gust of wind could be enough to cause problems. Here, the linesmen are caught in a spin after leaving the power line.